Well, hello and welcome again to our journey into number theory, and we're in the middle of the working on the proof of the of Dirichlet's theorem. And we finished last time by developing a technique called summation by parts, or Arbel summation formula. And our next step was that we wanted to show that this complex zeta function, minus 1 on s minus 1, can be continued to an analytic function that's now, it's analytic on the region S, where the real part of S is bigger than 0. We know that zeta of S is analytic for real part of S bigger than 1, and we're going to push the boundary back to 0. This will follow from the following theorem, 4.4, that is, for the real part of S bigger than 1, the moment, zeta of S can be written as S on S minus 1 minus S times this rather peculiar looking integral which has a fractional part of S up here in the numerator. Now the proof of this is going to use our Arbel summation formula. So here's the statement of the theorem again, and we taking real part of S bigger than 1, and we're going to show we can write zeta of S in this way. So as usual, we're going to write this S as sigma plus IT, and we're going to take sigma bigger than 1. And we're going to be looking at the zeta function. So I'm going to be writing zeta of S as 1 times n to the S. So in my Arbel summation, I'm going to take an is 1, that's going to be this first term, and the bn's will be the 1 on n to the s's. So to use Arbel summation, we have to add up an is the partial sums of the little a's. Well, that's easy, that's just n. We note also that an times bn, so if you multiply these together, then that will go to 0 as n goes to infinity, because the real part is bigger than 1. Now the applying Arbel's summation formula, then we simply get the following. So we sum this one, that turns into n, and we take this funny difference here with this, so that's 1 on n to the s minus 1 on n plus 1 to the s. Now this is looking a little bit like an integral, and in fact one is tempted then to write this as an integral. And so I'm going to write this then as the integral of s on x to the s plus 1 dx from n up to n plus 1. So if you integrate this, put in the endpoints and subtract, you of course get there. Now I'm then going to do the following. I'm going to take the s is independent of everything, so take the s right out the front, and I want to take the n inside the integral. Now to do that, remember that the floor of x is n if x is between n and n plus 1. So for x strictly in this interval between n and n plus 1, I can replace this n with the floor of x. And then I observe that the floor of x is x minus the fractional part of x. And so again I can replace the floor up here by x minus the fractional part. So that gets me to this stage. Well, now one is tempted, of course, then to split the integral into 2 bits, which is what I do next. And I'm going to get s times 1 on x to the s dx minus s times this fractional part of x on x to the s plus 1, integrating from 1 to infinity. This integral we can work out. This is easy. This is just s on s minus 1. And this one here we leave alone. And that's what we were aiming to prove. Now, the important point is that this integral, in fact, well, I know where does this converge? Well, if we look at the modulus of this integral, then the biggest that the fractional part can be is 1, so that's less or equal to 1. And we've seen before that the modulus of 1 over x to the s plus 1 is just x to the sigma plus 1. So x is real, of course, here, and the s is my sigma plus I. And the point is this integral will converge provided s is bigger than 0. And that's the important point. This integral now converges if s is bigger than 0. Because if s is bigger than 0, this power up here is bigger than 1, and we know that this improper integral then converges. So that's very nice, because that means the right-hand side of our expression then for zeta of s makes sense for s bigger than 0. And that is, we can now define zeta of s to be this expression, and this expression now makes sense for real part of s bigger than 0, and this is going to be then the analytic extension of zeta of s pushed back to real part of s bigger equal to 0. So, just to summarize that then, so for s bigger than 1, zeta of s agrees with this funny expression, this integral expression, and so we can define zeta of s to be precisely this function here, which is valid for the real part bigger than 1, s not equal to 1. Because if s equals 1, of course this doesn't exist here. In other words, zeta of s has an analytic continuation onto the region sigma bigger than 0, and this new zeta function now has a simple pole at s equals 1. Now we're going to try and do a similar thing for L of s and chi, where chi is not the principal character. We'll deal with principal characters later. So to do that we need a little lemma. So we take chi to be a non-principal, non-trivial, that means non-principal character modulo a, and we take any n bigger than 0. And I'm going to prove that the size of this sum, the modulus of this sum, is less or equal to 5a. So we can get a bound on the size of this sum of characters from n equals 0 up to any value n. You might just think about what that means. So we've got this sum up to capital N terms, any number capital N, and if we take the modulus of that sum, then the most we can ever get is 5a. So if chi is not equal to chi 1, so chi is not principal, I'm going to take my n and I'm going to divide it by a, goes q times with the remainder r, where r is between 0 and a. So I'm going to be using here, of course, the fact that these characters are periodic of period a. So we note that chi of n plus a is chi of n for all positive integers n. So I can take my sum, which goes from n equals 1 to a, and I can write it then as q times the sum up to a minus 1, n equals 0 to there, and then plus all the terms n equals 1 up to r. Now, this sum here, of course, is 0 because it's periodic. Sorry, not because it's periodic, because we've seen before that the sum of all the characters n equals 0 up to a minus 1 turns out to be 0. And so I'm simply left with this sum from n equals 1 up to r, and that's what we get left with. So I can reduce this sum n equals 1 up to capital N just to the sum of n equals 1 up to r, which is the remainder when I divide capital N by a. So that means now the modulus of this sum is the modulus of this sum, which is less or equal to the, just by triangle inequality, is less than the sum n equals 1 to a minus 1 of chi of n. And so I'm replacing the r here is certainly less than a, so it's less or equal to a minus 1. And again, we've seen that the sum of the moduli of these are all 1. So it's going to give me the sum of all of these, which is just 5a. It's the number of numbers relatively prime to a and less than it. So that gives me a nice bound on this sum, which we're going to need for our next slightly more technical theorem 4.5. Now this says if chi is not principal, then this series is convergent for the real part of s bigger than 0. And that's the important point. and the sum is analytic in that region. That is, for chi non-principal, this infinite series is going to converge. So that is, if chi is not equal to the principal character, then this thing is bounded as s goes to 1 from above. We have also to show that it's bounded away from 0. That's a bit more difficult. We'll have a look at that later. We're just showing this sum here for non-principal characters. The L functions are all bounded as s goes to 1 from above. Now the proof is slightly long and technical, but that's just the way it is. People have looked at the simpler proofs. There are various different proofs of this using different levels of machinery. I'm just going to do a fairly bare hands one here. So what I'm going to do is I'm going to analytically extend this L of s and chi, for chi not principal, to a function which is analytic for real part of s bigger than 0. Now we do that by, I'm going to start by looking at this sum. So we're looking at the Dirichlet sum n equals 1 up to capital N, a finite Dirichlet sum of the characters on n to the s for real part of s bigger than 1. And of course I'm going to hit this with the Arbel summation formula. So I'm going to take the a_n's to be the chi of n's, and the b_n's as 1 on n to the s. So this is somewhat similar to what we did a minute ago when we were looking at the zeta function. I'm going to try and model it on what we did there. So before we had an was 1, and now we've got it to be chi of n. So I'm going to set sx equal to be the sum of the characters evaluated at k for k less or equal to x, and I'm going to set s of 0 to be 0. So using Arbel's summation then, we're going to take this one as my little an, so I take the sum of these, and the sum of these is going to be s of n, and because here I'm replacing x with n, so I'll get the sum from 1 up to n, and then I take a difference on this one, so that's 1 on n to the s minus 1 on n plus 1 to the s. Now this is a finite sum, so we've got those extra terms left here. We've got that capital A sub n times b little b sub n, which gives me this, and then we have that other term at the beginning, but it's got an s of 0, and that's 0, so that term disappears. Now, as we did before, we're going to interpret this as an integral. So I'm going to write this now as the integral from n up to n plus 1, s on x to the s plus 1, just as we did in the earlier section, and then I've got an s of n, plus this term just copy down. Now what we did before is we took the s out the front. I'll do that again, and I want to bring the s in, the s of n, into the integral, so I'm going to write this as s of x, because now x is between n and n plus 1, so this x here will be just, the n is just going to be s of x, and then I copy that down and copy that down. All I've done here then is I now add up all of these. I now put n equals 1 up to capital N minus 1, and that into there, that's going to give me now the full integral from 1 to n of sx x to the minus s minus 1 dx, plus copy that down. And what I want to do now is I want to try and get a handle on how big this can be. So this one is, we'll see, is fairly easy to show goes to 0 as n goes to infinity. We'll do that in a second, but it's this one here we need to fiddle around with a bit. Now, by the lemma that we just had, we know that this sum of the first n values of chi of n is less than phi of a. That was our lemma. So that means the absolute value of the modulus, I should say, of s of x is less than phi of a, because this is independent of n. So therefore I can take the modulus of this integral that we had and now simply use properties of integrals. So this is less or equal to modulus of s, that goes here, modulus of this term, which is there, And the modulus of this, well, that's less than 5a, so I can pull that out the front. So this is now equal to 5a modulus of s, and the modulus of x to the s plus 1 is x to the 1 over that is 1 over x to the sigma plus 1. We've seen that before. And the point is that this integral here now converges. This will converge to 1. In fact, you can do the integration provided sigma is bigger than naught. This converges, and if you do the integration, you just get 1 over sigma times a term which goes to 0 as n goes to infinity, and then you'll get a 1 as well, and you get these terms surviving. So as n goes to infinity, this tends to 5a modulus of s on sigma. Sigma is the real part of s, and this works if s is bigger than 0, because this will converge for, sigma bigger than 0. Finally then, this last remaining term, the size of this, again, the size of s of n is less than 5a. This is bounded, and this again goes to 0 as n goes to infinity, provided s is bigger than 0. So what we've done is then, we've shown that this L of s of chi, which has this as its, well, this is the definition of it, this can be written then as this expression with the other term going to 0, and we've shown that this converges for the real part of s bigger than 0. So the point is we've moved from bigger equal to 1 to bigger equal to 0, and so this now defines an analytic continuation for L of s and chi to the real part of s is bigger than 0. And that's very good, because that means we're now inside the region where s is equal to 1, and hence that means this thing is bounded as s goes to 1 from above. And that's the key point of this particular theorem. The next stage of this is to now look at what happens to the principal character chi 1. So for the principal character chi 1, this L of s and chi 1 extends to a meromorphic function for real part of s bigger than 0, and it's got a simple pole at s equals 1, and indeed we can write this as zeta of s times this product, the product of the prime divisors of a, 1 minus 1 on p to the s. So p is understood, of course, to be prime. This is a finite sum here. So that means as s goes to 1 from above, this is a finite number, but this one goes to infinity. This is just our zeta function. As s goes to 1, this goes to infinity. And that tells me that L of s and chi 1 diverges. And that was another important step we saw in the earlier warm-up proofs to Dirichlet's theorem. So, little proof of theorem 4.6. This one's not very hard to prove, in fact. This one's fairly easy. So, you recall, this is what we're proving, that L of s and chi 1, if chi 1's our principal argument, this is zeta of s times this finite sum. And that tells me then that this diverges as s goes to 1, because zeta diverges as s goes to 1 from above. So again, let the real part of s be bigger than 1 for the moment. Then as before, we've seen before that L of s and chi 1 is, we can write using this Euler product. It's the product of primes that do not divide a, 1 over 1 minus p to the s. We've seen also before that zeta of s is the product over all primes, 1 over 1 minus p to the s. And so I can write this sum here as zeta of s, that's the sum over all the primes, divided by, so this is the primes that don't divide a, so I divide that by the primes that do divide a, 1 minus 1 on p to the s to the minus 1. And I can just pull that up the top, and I get zeta of s is the product over all the primes that divide a, 1 minus 1 over p to the s. And this, of course, as I mentioned, this is a finite product, and that means as s goes to 1 from above, zeta of s goes to infinity, so L of s and chi1 diverges. This goes to infinity as s goes to 1 from above. Now, the most difficult part of the Dirichlet's theorem, which is to show that if chi is not principal, then L of 1 and chi is not 0. We've shown that if chi is not principal, then L of s and chi converges, so its log is therefore finite. We need to show that as s goes to 1 of L of s and chi, that is, if we look at L of 1 and chi, that thing is not 0 at s equals 1, because we need to take a logarithm, and we don't want to be taking logs of 0 because we get minus infinity, and that might cancel out with other terms, and we want to make sure that this is finite, that the logarithm of this number is a finite number. That is, that L of s and chi is bounded away from 0 as s goes to 1 from above. Now, in earlier examples, the warm-up examples, we did some fancy fiddling around with inequalities and things to show that for particular examples. That doesn't generalise very nicely at all, and so we need a more sophisticated proof. And that's the most difficult part of the whole proof. And I'm going to just assume the result for the moment and finish the proof of the theorem. That is, we're going to assume that if chi is not principal, then L of 1 and chi is not 0. And then in our next section, we'll finish off with theorem 4.8, which is to finish off the proof of Dirichlet's theorem. We'll then come back and have a look at the proof of theorem 4.7.